Okay. Now, you remember last session we started with introducing the topic power electronics. We define the power electronics as a topic. We talk about linear power supply and switch mode power supply and what is the difference between them and how we need to save energy, improve efficiency, reduce size and weight. We give example and then we talk about the principle of power electronics and the four circuits: rectifier, inverter, AC voltage control, DC-DC converter, which is DC chopper, and how we convert from one shape into another shape, how we manage the power with the electronics through the control, and how we do the process. Also, we introduce the applications for power electronics. And let me tell you something at the end of this course, when we start with the applications, you will enjoy much, because I will show you what we are studying is applicable in industry and where you are going to face these applications. You will enjoy a lot in the part related to applications. Also, still introducing the topic, today I will, in this session, I will revise with you semiconductor devices, because we will need them. These are the main elements in our converter circuits. And also we will introduce a few more and some points to be highlighted related to these switches also to be mentioned here. So still introducing and revision for the course. Okay, maybe session number 3 will be more close, 3 or 4 will be more close to starting the power electronic converters. Still now revision and introducing the topic. Now, if I want to classify semiconductor devices, you remember semiconductor, we discussed them in level 2. We mentioned that semiconductor devices is, we use the semiconductor material, mainly silicon or germanium, today mainly silicon. And we make a doping impurities to have p-type, n-type. We put them together to come up with p-n junction, p-type, p-n diode. We talk about the characteristics at that time of the p-n junction diode, IV characteristics in third quadrant, third quadrant. All these have been discussed. Also, we discussed the transistor, which contain 3 layers, PMP or MPN. Also, this has been discussed, and we discussed the biasing, DC biasing, all these. Now, if I want to classify my semiconductor devices switches, okay, I will say, based on their control, they are either uncontrolled. Let me just check the color. Okay. Either uncontrolled devices, either on or off, which is represented by diode. Diode, we call it uncontrolled device. Why uncontrolled device? Because there is no way to control it. If the voltage in forward bias, it's on. If it's a reverse bias, it's off. We cannot control it. So we call it uncontrolled device. While control switches, these represent transistor, field, bipolar junction transistor, field effect transistor, MOSFET, junction field effect transistor, and other type of switches, control switch. We call them control. Why? Because we can't control them. As example, you remember transistor BJT. If we apply current across the base, the transistor will be on, right? It will conduct. If we remove the signal, it will be off. So we can't control it. For that, we call it control device. The same thing for field effect transistor. If we apply voltage across the gate, in BJT base, here it's gate. If we apply voltage, that in the BJT, we apply current. Here we apply voltage because it's voltage control device, if you remember. Okay? So when we apply voltage and increase it, then what we have? We have on. We can't control it. We reduce it, it will be off below the threshold voltage. So there is uncontrolled, which is represented by diode, and there is control, which is represented by, as example, BJT or FET or MOSFET and so on. And there is another one, which is in between almost. It's also on control, but need to be forced to be stopped. Have a look here. It's called thyristor. I will talk about it later on today, inshallah. Thyristor is another way. We apply signal, okay? When the signal enough, then and the voltage applied is forward voltage, it will be latched. It means it will conduct. We can control when to send this signal and when to start conduct. Without signal, even if the forward voltage is applied, the thyristor will not conduct. But when we send signal at specific time, it will conduct. Now these are main type of switch based on their degree of control, and it's been invented in 1950. And remember BGT, okay, Kirchhoff and his group, and then MOSFET came in this almost after 70. IGBT, isolated gate bipolar transistor, MCT. I will talk about them, revise them, okay, in this session. Also, just to remind you, diode represented by this symbol, okay, and we have anode on the positive layer, cathode on the negative layer. Current follow in one direction, in this direction, it cannot follow in the opposite direction, okay. And the IV characteristics, I, D, and VD, represented in quadrant 1 and quadrant 3. In quadrant 1, we call it forward bias. This is the curve. In third quadrant, if you remember, it is reverse bias, okay. This is the curve. And when we deal with it as a ideal element, no voltage drop, because here we have voltage drop, V on or VF, we call it, okay. When we assume that it is ideal, then there is no voltage drop, only current will follow. And in the other direction, there is no leakage current will follow, only voltage appear. So this is the diode, it's already discussed. If I classify diodes based on their specifications, I have the first type, which is called Shockley diode. By the way, diode family is large family. Do you remember we have Zener diode, light emitting diode, photodiode? We discussed them in level 2. But here I'm trying to classify the main based on their rating and their applications. The first one is Shockley diode. Shockley diode, if you can see here, have low forward voltage drop. The voltage drop is small, around 0.3. Okay, you remember it should be 0.7 and above. 0.7 for silicon, 1.2 for germanium. But here in this type of diode, it is around 0.3. This is useful in application which need small voltages. Okay, we deal with small voltage, because if the voltage is high and the circuit voltage is small, then the losses will be high, the drop will be high, and it's not preferable to deal with this type of diode. It's preferable to use small voltage drop in small circuit voltage diode. Also, its capability, the voltage, its voltage is small, as you can see here, between 50 to 100 volt. Another type of diode is called fast recovery diode. This one, from the name, fast recovery, okay? It's used in fast speed or high speed circuits. Its voltage and current is a little bit higher comparing with the Shockley voltage and the current diode. You can see 100 volts, several hundred ampere. But it's fast. It's fast in operation. So the first one have low voltage drop. The second one is faster than the first one, but higher voltage drop. The normal or the conventional one, which is available in the market, and mainly we are dealing with it in the lab, is the line frequency. It's normal diode, the one available you can purchase online. Its rating is from small voltages to medium to high voltage, even approaching kiloamp and kilovolts. Okay, and it have high voltage drop, which around 0.7 and above. One point now, until now, maybe the information is no, you know it. Okay, I just revising, but here I would like to add something. Yes.
دكتور من فضلك لو تظهر لنا السلايد بنفسه، يعني انت مظهر صفحة اللابتوب كاملة، ما يظهر عندنا واضح.
Okay. Just a minute. Sorry. Okay. 1 second. Now you can see the slide better.
Yes.
Doctor.
That's great. Now Just a new point I would like to define here is the turn off. Also, I would like to remind you, do you remember BGT? We discussed the level 2. We mentioned in BGT, we discussed it at that time when it worked in active region. Active region is mean we amplify the signal. It works as a variable resistance. Also at that time, I mentioned for you that there is cutoff region on horizontal and on vertical, we have saturation region. I told you at that time, if you remember, that in these two regions, the transistor work as a switch. It's not an amplifier anymore. Not amplifier anymore. It's work as a switch, either on or off. And I told you at that time, if you remember, we will discuss this situation in our converters in level 3 in power electronics. Anybody remember this discussion? Anybody? You don't remember? Okay. Okay. It doesn't matter. It doesn't matter. Okay. Now, here in this course, we will use these switches, I mean, diode, transistor, thyristor, as switches only. It means no amplification, either on or off. That's it, done. Okay. Now, because of this, it is a switch either on or off. We look for the energy losses. We look to the speed. It's important. So one of the points I would like to mention here is the reverse recovery. What is reverse recovery? Have a look. Let's assume the diode was conducting the current. This is ID. Then at specific point, the voltage reverse bias. So the diode current should go to 0 and the diode will be off, open circuit, right? Agree with this? I want response. Agree with this? Should go to 0. Great, great. So the current will fall down until it reaches this point. When it reaches this point, doesn't mean that the current now 0. The diode is totally off. It needs some time which called TRR. TRR, reverse recovery time. What does this reverse recovery time represent? You remember the diode? This is the diode. This is P, let me say this is N. You remember here the layer, okay, the junction, sorry. Sideband of the junction, there is positive and negative charge. You remember them. These charge need to be removed and recombination happen. Okay, so what happened? The current here will go down in the negative direction until it reach the IRM, reverse maximum current, and then it back to 0. This charge QRR will disappear. Okay, the charge here and here will disappear. When it disappears and we reach this point, current becomes 0, no charge in the junction. We will say now the diode is turning off. So this time TRR need to be considered when we design our converter circuits. We need to consider reverse recovery time. As small as the reverse recovery time, which means better switching off, because the time required to cancel charge here is a small time. So now reverse recovery time, I think it's clear. When we switch off, the current will go to 0, but it needs time to the charge inside the junction to be recombination happen and recombined, and this take time, which is called reverse recovery time. By the way, reverse recovery time is very short time. We're talking about sometime in microsecond, very small time, okay? But it's counted. Its effect in the circuit, I will mention for it later on, inshallah, it will appear. We need to consider it in our design. Now I completed the revision for the diode. Let me start with the thyristor, another device, semiconductor device. Now you remember PN junction is the diode, okay? And the transistor, if you remember, PNP or MPN is, let me say MPN, okay? 3 terminal and 2 junction. This is junction 1, junction 2. Now there is another device which is called thyristor. Thyristor is 3 junction, 4 layers, PN, but also a 3 terminal device. Okay, but 3 junction, junction 1, junction 2, junction 3. Okay, and let me tell you something, at the end we are using semiconductor silicons, okay, material to manufacture all of these type of silicon devices, semiconductor devices, but their characteristics, their operations, their function, their performance is different. The same material, but the way of manufacturing is different, which produce different characteristics. How it look like the sample? This is the sample, but I will sketch it again. You can see here. It's similar to diode from this direction, but here you see here, this is anode, cathode, anode, and this is the gate. Gate here to this point connected. We send here signal, sample, pulse, small pulse to the gate here. Here the gate. We send sample, small signal. When we send it, it will conduct. It means without sending the signal, even if the voltage is positive voltage, positive here, negative here, we apply forward voltage, the thyristor will not conduct until we send the gate signal. Okay, for that, its characteristics IA versus VAK, I emitter, okay, I anode, sorry, versus V anode cathode. We can see the forward bias, the reverse bias is the same, but forward bias depend on what? Depend on the signal. When signal come, it will conduct. I will show you later on today. But when signal come, it will conduct. When there is no signal, it will not conduct. This is how it look like the thyristor. This is the sample. This is how it look like in the market. Different shape, different size, different rating. I make here a link for you just to see the different type and their specifications. Now, you see here, when I put thyristor in a circuit resistance with supply AC, now the voltage here, if you can see from 0, it will be increased. The voltage of the supply is forward voltage. But you can see the thyristor will not conduct. Zero voltage, zero current appear across the load. It will not conduct until we send pulse. Here at this point, we send pulse. What will happen? There is voltage, which is forward voltage, and there is pulse coming to the gate. The thyristor will conduct. You see, so the voltage of the source will appear across the load for the first half part. And if we divide voltage over resistance, it gives me the current. Now, when the voltage become reverse bias, the voltage and current will go to 0, similar to the diode. Because two things need to be there. So we can't say the thyristor will conduct in forward bias. The first issue is the voltage, forward voltage is there. There is voltage which is forward in the forward direction, plus, okay? There is pulse coming to the gate. When we have these two conditions, the thyristor will conduct, otherwise it will not conduct. Okay. This is the general. But because the thyristor have family, they design different type of thyristors. Some of them work based on light. Some of them work based on the voltage. I mean, they increase the voltage until it reach high voltage, then it will conduct. Okay, and so on. So different voltage, a different type of thyristor are available in the market. If you want more information, I advise you to read the textbook Power Electronic Principal Device and Application by Muhammad Rashid, or even you can read in my book. I have book all time back I publish in Power Electronics. Also, I make a details on these type of thyristors and their pulsation. Now, also let me classify thyristor based on their rating, how much the voltage we can apply across them and block, and how much the current they can conduct. So the first one is called phase control thyristor. Okay, this type of thyristor conduct up to 4,000 ampere, block 5 to 7 kilovolt. So it's used mainly in power plants and in industry. The second one is inverter grade thyristor. Its voltage is lower, its current is lower, but still in thousands. And the light activated thyristor work with high voltage and high current, but it's activated by light. It means we apply light rather than on the gate. We don't apply pulse, we apply light, and the light will make the thyristor conducting. One more issue here to be mentioned. You remember I talked about the reverse recovery time for diode. The same thing happened with the thyristor. We need to consider reverse recovery time. This is, as you can see here, current was following here, and then we switch off. At this point, current will need to be reversed to take time, which is called reverse recovery time. The charge inside the junction will remove. But this is not enough. Why? Have a look. Have a look. This is my thyristor. 3 junction, P, N, P, N. Okay? Let's say this is anode, this is the cathode, this is gate. When we change the voltage to become reverse bias, negative here, positive here, these definitely not reverse bias, these junctions will take time called reverse recovery time to recover the charge in the junction. But the internal junction need more time than this, because the voltage here and voltage here are not reaching it. So it needs more time. So the voltage need to drop slowly and take its time, as you can see here, until it reaches this point. The voltage become 0 across the thyristor. This is TQ, we call it T cutoff time. Now, when we deal with thyristor, we need to consider cutoff time rather than reverse recovery time. Yeah, it means we don't say that the thyristor is off now when TRR reached. No, we say it is off when TQ reached, which is higher than TRR. Otherwise, if the voltage, if we don't reach here, as example, if we at this point we say the thyristor off, not at this point, what happened? If the voltage changes direction, this become negative, this become positive. No need for gate pulse to work. Why? Because the thyristor is not off yet. Pulse is coming one time, small pulse for a small time, maybe in millisecond or microsecond, and we remove it. Okay? But here, when I try to switch it off, reverse recovery time doesn't tell me that my thyristor is off. I need TQ to make sure that these junctions have recombination and reverse recovery time applied there and the charge removed, and the internal junction take more time to remove the charge until it gets 0. Then we call it reverse TQ cutoff time. Now I will discuss this in more details through the circuits. When we design our circuits and we discuss their operation, we will mention for this at that time. Now this is the simple for thyristor. It could be, you remember, transistor, we represented by 2 diodes, if you remember, in level 2, either opposite or face to face, right? In this way. The thyristor could be represented in 2 transistors, connected to transistor in this way, or in this way. Okay? Or 4 diodes. Now, I revised the diode principles, characteristics, idea. I discussed the thyristor. Maybe you didn't discuss it before. Now let me discuss the generic switch. Generic switch, I put it as a name, generic switch, because it contains BJT transistor, field effect transistor, MOSFET, isolated gate bipolar transistor, gate turn-off thyristors, different type of semiconductor switches. These can be controlled. We represent it as a switch, simply as a switch. Okay. Now you remember last session. You remember this circuit from last session. Okay. I will use it. I will use it to explain. Okay, what happened when we switch on and switch off the transistor, the thyristor, the diode? What will happen? Okay. Let's have a look here. Let's assume, you see here, this is diode. Just follow me here because I will explain on this graph. And this is switch. Okay. Now the switch was open. When the switch open, current follow through the diode in this direction. Okay, just following here. When we switch on this one, now the supply will provide the current and follow here. It cannot follow here in this direction. The diode here will be reverse bias, will follow here and here through the switch and back to the supply. So the voltage was 0, off, it become on. Okay, easy. Now off, on. This is the switch signal. Okay, now let's see what happened to the switch. If it is thyristor or whatever it is, what happened to the current and voltage when it converts from off to on? When it was off, no current will follow, 0 current, open circuit. When on, full current will follow. So the voltage, when it's off, the voltage is high, blocked voltage, and small current, and vice versa when it become on. So at this point here, the voltage was high, the current was 0, open circuit. And now the voltage, the switch at this point, you can see here, at this point, will be on. What happened? The current start increase gradually in this way until it reach maximum current. Okay, now it is on because it's conducting the maximum current, I output. While the voltage, okay, it's still high until the current reach high, the highest current, then the voltage will go down until it reach small voltage, which is called V on or V drop voltage. Okay, voltage drop 0.7 volt around this value, and it will continue because now we are in on state. You see this triangle, the first part of the triangle I will call it TRI. It means rising time for current, while here TFV, falling time for voltage. The current increase, the voltage decrease. And if I come to add these two times, I will call them TC on, the switch on time. Okay, the same triangle will appear here when I switch off. The voltage will increase now to block until it reaches maximum voltage. The current will fall to 0. The same triangle. Okay, this triangle happened when I switch on and switch off. Okay, when I switch on, as you can see here, there is triangle. When I switch off, there is another triangle. Now the energy consumption when on and off is high comparing with the energy consumption when it is on time. You see here in on time? Yes, if you look to the power, let me simply power. I multiply the current here by the voltage here. It gives me small power. Why? Because the voltage is small. But here in these triangles, I can multiply current and voltages. The power will be high because both of them are high, current and voltages. So this is a problem. The problem is, again, to summarize the problem, is when we deal with power electronic circuits, converter circuits, we deal with the semiconductor switch to work as a switch on or off. That's it, done. But the problem here is when you switch on and switch off, there is heat, energy dissipation need to be dissipated. So it's power losses, it is heat at the end. So this is a problem. We need to switch on and off many times and very fast, talking in micro or millisecond. It means this triangle will appear many times. So many times we have losses. We have high heat need to be dissipated. This is a problem we need to consider. Okay, yes, today you may say, okay, today technology, the lifestyle of today technology, our laptops, our mobile smartphone, our tabs, our lab, all of them working very fast. The speed is high, the frequency is high, right? And this high work, okay, very fast speed, this will, from the other side, make my triangle appear many times in my circuits, which mean high losses, high power dissipation. This need to be considered. Otherwise, we may lose our semiconductor switch. It may burn. We may lose the transistor, the thyristor, and so on. So let me summarize from this discussion the formula. T on for the switch contain T rising for the current and fail for the voltage, these two. And if I want to calculate the energy, it's 1/2 voltage times current times this time, TC on, which is this one. Now for T on, okay, yes, T on, the time needed here, from here to here, is high. The current is high, but the problem is voltage is small. It's not a problem, it's good. Because when the voltage is small, this power will be low comparing with this power. And the same thing could be said for T off. T off, as you can see, is rising voltage, failing of current, and the power dissipated will be 1/2 VI by the time. Now, if I add P on, it will be V times current, which is power, multiply by T on over TS. T on is the on time from here to here, while TS is the total time, which contain on and off plus the T on, the total time. Let me now revise BGT. I'm around to finish. BGT, you remember BGT is a 3. Yes.
بالنسبة للقوانين السابقة هل نحتاج لهن قدام يعني أو بس كتوضيح؟
No. Now you will use some of them. You will use in tutorial. I will use some of them. Okay. But look, in power electronic, we will design circuit to do some functions in industry, as example. You will learn how to design the circuit, and at the same time you will learn how to control and operate the circuit and how to protect the circuit. This information now is related to how you protect your circuit, okay, and how to operate your circuit. We will use them in some places through the semester. I will show you, okay? You have the formula. At this time, I just want you to understand what these equations, from where it came. With example, it would be very easy. And now I'm focusing only on the theoretical part. The first 3 sessions, 3 hours, this week and next week, the first session also, is just introducing the topic, power electronic. When we start with the power electronic circuits, you will enjoy more. And you will find that this revision is useful. I'm revising. Now BGT, we discussed it in level 2, if you remember. We say that it's 3-terminal device, collector, emitter, and airbase. We discussed DC bias, IV characteristics, the output characteristics, input characteristics was between I base with V base emitter, output characteristics between I collector, V collector emitter. We classify the element parts here. This is the active region, this is the cutoff region, this is the saturation region. All this has been discussed. I just here want to mention and remind you. This is how it look like in the market, and I make link here for you just to go and see different type available in the market. Okay, we can also connect them in Darlington, as you see this has been discussed before. And also I discussed MOSFET. If you remember in level 2, we discussed MOSFET. Drain, source, gate. We mentioned that this is a voltage control device comparing with BGT, which is a current control device. We classified here that this is the triode region, this is the saturation region, this is the cutoff region. We talk about how we control the BGT, what are the different, MOSFET, what are the different type of MOSFET. We discussed the DC biasing graphically and by calculation, how we analyze the circuit contain MOSFET. I'm just reminding you here. And another type is what we call a GTO, gate turn off thyristor. Gate turn off thyristor, you remember the thyristor I just discussed in the previous slides? I mentioned in the thyristor, we need to apply forward voltage and signal pulse to the gate so it will conduct. But to make it off, what we need, reverse voltage, and we need to remove all charge inside the junctions to be off, which is taking time, which is called TQ. But some application you need to specify the required time to be off and the required time to be on. As example, in DC circuits, the voltage will not be reversed. It's all the time forward direction. So what should we do? We use this type of thyristor, which is called gate turn off thyristor. Gate turn off thyristor is different now. You can see these arrows, one in, one out, which tell me the in will switch on, the out will switch off. So this type of thyristor, we can control also the switching off. It's like another element or another family member of the thyristor. Okay, you can see here, turning on in this direction, turning off in this direction. This is how it look like, this turn off, gate turn off thyristor, and it's available. I make a link here for you for more information. And we will see that gate turn off thyristor, we need to protect it. Later on at the end of this semester, maybe the last session, I will talk about snubber circuit, protection circuits, okay? Because in this type of thyristor, because of the fast switching on and off, we have a problem of dV over dt and di over dt. We need to protect. I'm here just mentioning. Also, these are what available in the market. I make a link for you for more information. One more is IGBT, isolated gate bipolar transistor. It's bipolar transistor, but isolated gate, okay? Look, as I told you, we use semiconductor, the silicon, but we change the way how we manufacture it. We change the steps inside the manufacturing line production. We change the way how we make a doping. We come up with a new element to be added, which gives different function. Now IGBT, it's like improving in the characteristics. IGBT, isolated gate bipolar transistor, is a transistor which have its characteristics between MOSFET and gate turn off. We compare it with MOSFET, it has a small amount of energy, consume less energy. While when I compare it with BGT, BGT have a smaller, BGT compare like BGT, it have a small on state voltage drop is small, okay? And similar to GT off, it have a blocking negative voltage, can block negative voltage. So manipulating the way how we manufacture the semiconductor switch, we come up with different characteristics. This is also what is available in the market. Usually it's have application in high rating voltage, current and power, especially in industry to control, as example, the operation of motors, okay, induction motors. Now last one, and I will conclude, is MOS control thyristor, okay, MCT, MOS control thyristor. Now this one is another type of thyristor. Also, they improve most of the GTO properties to come up with another one which have a different characteristics. Okay, also it can turn off and on using signal in this way. Now these are some main type of semiconductor switching. In this revision, I introduced to you some different switches. These switches, this is the conclusion. These switches are different in their power capability and the switching speed, the speed and the power rating. As example, we can see that BGT, its power rating is medium, its speed is medium. But when we go to MOSFET, it have lower power capability, but it's very fast. So if I'm looking to these properties, low power capability and fast speed, definitely I will go for MOSFET. I will not go for BGT. And vice versa. The same thing for GTO, GBT, MCT, they have different rating. And because of different, if I put them here, the voltage against the current, against the frequency, if I'm looking to high speed frequency, then MOSFET is the best. If I'm looking to high current and voltage, thyristor is the best. So you need to look, what is your application? What you are looking for, okay? Look to the application, you specify which switch to collect or to use. Now let me summarize this week sessions, live sessions. Next session today, this week, inshallah, it will be tutorial. We will start solving a problem. But here, let me summarize. In these 2 hours, okay, we introduce the power electronic as a topic. What is the environment of power electronics? What we need to study power electronics? What are the circuits to be studied in power electronics, the 4 circuits? What is the comparison between linear power supply and switch mode power supply, which use power electronics converters? Okay. What are the applications? Yesterday we talked about the application in different sectors: industry, in power plants, in let me say office appliances, in homes, in buildings, in space, and in transportation. And today we revise the semiconductor devices. We revise the diode. We revise the BGT. We talk about thyristor. Okay. We talk about isolated gate bipolar transistor, gate turn off thyristor. Also, we talk about the losses when we switch on and off. We say there is 2 triangles: when on, when off. These losses we need to consider. Yes.
Please, I have a question.
Yeah, I'm finished. Yeah, I'm listening to your question. Please. Yeah.
Please back to that previous triangles, that graph.
Okay. Here, yeah.
Yeah, this one.
Yeah.
Sir, how the equation come to this bar? And
I will.
If
Yeah, please.
necessary to know how to draw these triangles.
You don't need to draw them.
I will draw this.
No, you don't need to draw them. I will solve a problem using these equations. We need, as example, I will show you. We need to calculate as example, the energy, okay? Energy consumption in on switching, in off switching. We need to know how to calculate them. We need to calculate the power of switching, the power of on. So usually these values, you have them. You just need to substitute and calculate them. Then later, when we calculate them, we can't discuss, we select this transistor or this transistor. So it's every merit of substitution. You don't need to drive them. I drive them for you. It's ready. You have them. In the example, I will clarify this. I will give you in the tutorial some examples to clarify this. Okay?
Okay.
Any more questions? By the way, the problem solving.
The important.
Sorry?
What is we need to know the important things from this week, which we have to know, or we focus.
Just revise the material I gave. Here it's just merit of introduction to the topic and revision. I mean, don't expect I will ask you as example, what is the power electronics? You know now you have the power electronics. You don't need to ask. I will ask you later on circuits, design circuits, but these are, let me say, introduction. I introduce the topic, I revise semiconductor. Later on, I don't expect from me as example to ask you, please sketch the diode simple. You know the diode simple, how it work, how the diode work. I don't need to ask you how the diode work, because you know, I just revise it now for you. This is revision on semiconductor devices. Still, next session, inshallah, next week when I start with the live session, I will also revise some important things related to AC and DC, single phase, 3-phase, electrical power technology. I will introduce the harmonics, some indexes, power factor, displacement power factor, total harmonic distortion, crest factor, and so on. So I will still introducing the topic. After that, I will start talking about the circuits. When we start with the circuit, you will enjoy because you will deal with the circuit directly. But you need to know what is the diode, how it works. We already studied this, but I revise it for you now. By the way, I've been teaching this course since 1997. Okay, it's my specialty, power electronics. So you will enjoy because I will give you from my, let me say, experience in industry a lot. I will talk about the industry, what you will face there, what you will see. Unfortunately, we have pandemic. Otherwise, I will take you to the industry to show you these components and these circuits in industry and how they use them to control either a chemical reactor or to control motor, induction motors, or induction oven, and so on. Okay. Hopefully you will enjoy this course. I'm sure there are many applications which make you enjoy with time. Let me stop here. Okay, we'll continue our discussion in the next session. Do you have any question?
But Victor, we need to focus more. How will be able to answer the exams?
With the tutorial, we will solve more problem. In theoretical part, usually I don't solve problem. I just give the brief of the information required for theoretical part. But when we go to the examples or problems to be solved in tutorial, you will learn how to deal with the exam. Also, I will try to make mock exam, which is try before we start midterm. I will upload it in the SULMS and you will access and then learn how to solve it, how it look like, what you expect from the exam to be, right? So I will train you. Don't worry. Don't worry. Let's stop here. Have a nice day and see you in another session. Bye-bye.